Good afternoon, dear students. This will be the last topic for us to cover. This topic will be divided into two parts. The first part will discuss the structural design, structure, and property relationship. We will discuss in detail about the influence of mesogenic unit, spacer, backbone, linker unit, and terminal group to the mesomorphic properties. Then, we review briefly the difference between main chain and side chain polymer liquid crystals. Finally, we will discuss how side chain polymer liquid crystals differ from low molar mass liquid crystal. There are various designs that have been identified for side chain liquid crystal polymer. The general template for side chain liquid crystal polymers are shown on top of the slide. The first is terminally attached, which means the end part of the mesogenic unit is attached to the spacer. The second is laterally attached, which means the side part of the mesogenic unit is attached to the spacer. The mesogenic group can be calamitic or discotic shaped. Polymer liquid crystals also exist as combination of main chain and side chain in one polymer, as illustrated in Figure A and Figure B on the slide. Side chain mesogenic units can be attached, via a spacer unit, to a mesogenic main chain either at the linking unit as shown in Figure A or at the mesogenic unit as illustrated in Figure B. The structural design for side chain liquid crystal polymers is shown in the blue box. There are 5 components that make up the structural design for side chain liquid crystal polymer. These are linking units, backbone, spacer unit, mesogenic unit and terminal group. It can be a homopolymers or copolymers. A homopolymer is a polymer where every monomer unit of the chain is the same as shown in example 1. Design 2, 3, and 4 are the example of copolymers. Design 2 is side chain copolymers, where it has different mesogenic unit. Design 3 is backbone copolymers, where it has different backbone. Design 4 is the combination of side chain copolymers and backbone copolymers. Now, let's discuss each important component in side chain polymer liquid crystals. We start with mesogenic unit and the influence of mesogenic unit to the mesomorphic property. A template structure for possible mesogenic side chain units is shown on the slide. The possibility of A, B and X are listed in the table and M and N are usually 1 or 2. Let's see the influence of different length of mesogenic unit. The increased polarisability and increased molecular length in going from N equal to 1 to N equal to 3 phenyl rings considerably enhances the clearing points of these nematic polymers. The clearing point is increased from 61 degrees Celsius to 319 degrees Celsius. The nematic phase is probably exhibited in preference to the smectic phase because the spacer and terminal chain lengths are short. Polymer become more crystalline as the mesogen length increases. Again, this is expected. When N equals 1, no crystal observed. When N greater than or equal to 2, the polymer is in crystalline state. Spacer is the link for attaching the mesogenic group to the backbone of the polymer. Slide shows the examples of spacer. It can be based on alkyl, alkali, or ester groups. The influence of the flexible spacer that is normally essential for the generation of mesophases in side chain liquid crystal polymer is of great interest. In general, the increased ordering generated on polymerization means that smectic phases predominate and the nematic phase is only exhibited by polymers with a short spacer and a short terminal chain. We use methacrylate polymers on the slide as an example. Let's see what will happen to the mesomorphic properties when increasing the spacer length, N, from N equals 0 to N equals 11. When N equals 0, they are of the smectic type. However, a short spacer such as N equals 2, usually generates a nematic phase. Longer spacers such as greater than or equal to 6, gives way to the smectic phases as the spacer length increases. The third component is the backbone. The top examples are the common backbone but non-mesogenic polymers. The methyl group or the X could be the point of mesogenic unit attachment. The two examples on the bottom of the slide are the unusual polymer backbones that been used in side-chain polymer liquid crystals. Let's see the influence of backbone flexibility on mesomorphic properties. On this slide, three different types of backbones, which are methacrylate, acrylate, and siloxane. These backbones are attached to identical spacer and mesogenic group, which is simplified as R on the slide. As we can see here, glass transition and the clearing point values fall with increasing backbone flexibility. Now, let's see the influence of the linker to the mesomorphic properties. On the slides, cyanobiphenyl was used as the mesogenic group. Cyanobiphenyl units have commonly been incorporated into side-chain liquid crystal polymers in order to generate polymers with a positive dielectric anisotropy. Polymers 1 to 3 differ only in the unit which links the spacer to the mesogenic unit. Polymer 1 has a particularly high clearing point because of the enhanced polarizability, whereas removal of the ether oxygen in polymer 2 has reduced the clearing point. The clearing point recovers by the use of an ester linkage for polymer 3, but not to the level of polymer 1 because of the kink in the structure. Glass transition temperature relates to the polarity of the connecting unit, highest for the polar ester in 3 and lowest for the hydrocarbon in 2. Let's see the influence of terminal group to the mesomorphic properties. Look at the acrylate polymers on the slide as an example. We vary the terminal group as indicated in the table. In general, increasing the alkyl chain on the terminal unit will increase the clearing point of the polymer. Now, we look at the difference between main chain liquid crystal polymers versus side chain liquid crystal polymers. In main chain liquid crystal polymers, the orientational order of the mesophase results from the near parallel alignment of the polymer main chain. Whereas, in side chain liquid crystal polymers, it is the mesogenic side groups and not the polymer main chain that display orientational order in the liquid crystalline states. Thus the polymer main chain does not itself need to have long-range ordering. As a result, they are much more like conventional amorphous polymers or plastics in their mechanical properties, being flexible, and can be easily processed using conventional technology into this films and other forms. They do not show the unusual mechanical properties of main chain liquid crystal polymers. In most respects, these polymers behave very much like the low molar mass liquid crystals. For example, they respond to an electric or a magnetic field. There are, however, some important differences, which give side-chain liquid crystal polymers unique electro-optical properties. The organization of the mesogenic group in a nematic phase of a side-chain liquid crystal polymers is as illustrated on the slide. The preferred directions are indicated by the arrows. In the nematic phase, these mesogenic side groups tend to point along a preferred direction, very much like conventional liquid crystals made of small molecules. The two major differences between these polymer materials and the low molar mass liquid crystals are: although the director alignment is readily attainable in the low molar mass liquid crystals, it is more difficult to align the director in the polymer materials. To induce director alignment, the materials must be submitted to a very strong electric or magnetic field, or thermal cycling through the isotropic phase in the presence of an electric/magnetic field. This precludes their use in active display devices. Unlike the low molar mass nematic and cholesteric liquid crystals, once aligned, the materials remain aligned for months to years even in the absence of the aligning electric or magnetic field, because the chain cannot move about easily as the liquids are extremely viscous. The sample must normally be heated to above clearing point to destroy this alignment. Side-chain liquid crystal polymers have tremendous potentials as high-value polymers because they are essentially hybrid systems, in that they exhibit the usual electro-optic properties of the low molar mass liquid crystals, while at the same time showing many of the physical properties of conventional plastics. This combination of properties can be exploited in a number of ways in the realization of new technologies. We will continue on the relevance of SCLCP in the area of optoelectronics in our next lecture.